let's say in this one, the stereochemistry of that center is the S. It's mixed. It's mirror image form. You've got the R1. Okay. So an example of that, so what I'm saying is they have this carboxylic acid. Okay, lactic acid, but it's mixed with this one. 50-50. Okay. What we're now going to do is mix with it an amine. Okay? And this is an amine that we've got as one enantiomer. So we're trying to separate this mixture of carboxylic acids, but thankfully we've been able to get the hands on a single enantiomer of an amine. Okay? And arbitrarily I've called this the R1. So it's going to be an R, the stereochemistry of that particular amine. Okay? Now those sorts of things can come from nature. Mother Nature provides us with lots of chiral amines. An example of that would be something like strychnine or strychnine, say in North America. So rat poison is actually a naturally occurring chiral single enantiomer of an amine, and they're actually commonly used to separate the enantiomers of two carboxylic acids. So we're going to take half the equivalent of this and half the equivalent of that and mix it with one equivalent of that. Okay? So what's going to form is you're going to form a salt between that one and that one, and a salt between this one and this one. So this is showing you the two salts. Okay, so in both cases, of course, it's the same chirality of the amine, and this is the two carboxylic acids. Okay? So now you have a product that either has SR or RR stereochemistry. Okay? So these differ at one site. It's a salt, okay? And they differ at the stereochemistry at one position. So these two salts are diastereomeric. Okay? They're different diastereomers. And so these are going to have different physical and chemical properties. So, fingers crossed, you often have to do a little bit of experimentation and fiddle with solvents, but you can preferentially get one of these species to drop out of solution. It will be the least soluble diastereomer that falls out of solution. Okay. So you've done this reaction. Say you did in ether, and what you observe, okay, would be some solid that you precipitate. Okay? So that solid is going to say be one of the diastereomers, but it leaves in the solution the more soluble diastereomer of the solid. Okay? So what you would do is filter this, and so the solid that was precipitated, okay, would be enriched in one of the carboxylic acids. Okay? Is everybody following me? Okay. So I'm saying you can physically isolate based on different physical and chemical properties of one of the diastereomeric salts. Okay? So you've separated these two enantiomers by forming diastereomeric solids. But now the question is, how do you get the carboxylic acid back? So you've separated. So now if you have HCl, you're just going to do a little bit more acid-base chemistry. This is a super strong acid. So it's going to go and protonate the conjugate base of the acid. Okay, so that protonates this one. Okay? So this could be washed out with water. It's still a salt, so you can recover the amine as its protonated form. You take that into the aqueous layer. But this, now being a neutralized organic compound, will be soluble in the ether layer. So you just do an extraction chemistry, the same thing you're doing in the lab. You'll be able to get that compound, you dry it and evaporate it, and you get one of the carboxylic acids. The filtrate separated it, and that will give you the access to the enantiomer. So can you follow that? Okay, I'll put some problem set questions in to see if you can get it. That's how you chemically resolve things. Biological. Perhaps this is a little bit easier to realise, okay? What nature provides us with is enzymes that are derived from chiral molecules. So they're all made from alpha amino acids. Okay, so enzymes, proteins are themselves chiral. And so these biological molecules can be used to resolve racemic mixtures. Okay? So for example, these are esters. Okay, so it's a racemic mixture of two esters. You've got 50-50 of these. What you can do is feed this to a biological system. And one common one would be pig liver esterase. Okay, so the biological people can isolate this protein from pig livers, and then you can use it to do chemistry. That's what nature uses protein source to do chemistry. Okay? Now, pig liver esterase is derived from chiral molecules. It can differentiate between these two. So what's going to happen is only one of them will be hydrolyzed. So one of these substrates, one of the enantiomers, would be preferentially digested. So you can think of the enzyme as being some sort of Pac-Man thing that comes around chewing up various proteins. But it can only fit like left hand shape, right hand. It can only fit certain molecules. So this one would digest this particular enantiomer, but wouldn't touch this one. Okay, so you'd be able to recover that from the reaction mixture when you've got a pure enantiomer. As I was saying, to get your hands on pure enantiomers of compounds isn't easy. It takes time, money, and expense. But the properties of enantiomers in biological systems can be very, very different because we are in ourselves handed. Okay, the last one is goes back to the history of, or the discovery of chirality in the first place. So, physical method. And this is really, it is a physical method. Okay? Just go back up to what I showed you earlier. These two things. These are the two enantiomers of tartaric acid. I think you can get it naturally as from fruits and vegetables. Okay, so you can isolate these two. And when you isolate them, it's a racemic mixture. Okay? You get a mixture. So what Pasteur did, the same person that developed the pipette, also did many other things. But what he did is he got his hand on this as a racemate, a 50-50 mixture, and he crystallized it. He was an expert in crystallography, growing crystals. So he grew some very nice crystals from this racemic material. Okay? And then with the microscope, he looked at the crystals. Okay? And what he noted is that the crystals were mirror images of one another. You could see a left-handed crystal and a right-handed crystal. So with tweezers, he separated the left-handed crystals from the right-handed crystals. Okay? And then he put the left-handed crystals in a polarimeter and found the rotating plane polarized like one direction. And the crystals he put right-hand ones seem to rotate the opposite direction. So certain compounds crystallize into what are called chiral space groups. Okay, so they pack, actually giving a crystal that's also asymmetric. And so that allows them to physically separate. And it turns out only one enantiomer forms a left-handed crystal, so the other enantiomer forms a right-handed crystal. So they were physically separated. And this was the discovery of the handedness of molecules the very first time. Right, I'll just tell you what we're going to be up to in the next couple of lectures. And then we'll wrap up for the day. So I need to do a bit of reading ahead. So we're going to talk about spectroscopy. Okay. And the textbook lists 4 types, A, B, C, D. Okay. The first one is IR, spectroscopy. The second one is UV vis. Third one is 1H NMR. And the fourth one is mass spectrometry. Okay? Now here's the good news. That one and that one. Okay? This is to do with the electronic structure of molecules. Okay? Why certain things are coloured, like your t-shirt being red, is the basis of organic molecules in lines. They're absorbing light and not absorbing enzymes. Okay? The basis of vision is all to do with molecules being absorbing light. Okay? That's in 281, 282 and 283. Mass spec is a way of measuring the mass of molecules. These are the ones I'm going to talk about that in the next lecture. Infrared spectroscopy. That's talk about how one red